Well, hello physics people. Welcome to Doc Ontko Physics. Keith Ontko here. And this is the first of 3 lessons that have to do with magnetic fields and forces. I'm breaking it up into 3 lessons because otherwise it would be one long lesson. It would probably be about 40 minutes long and no one can really tolerate that. So I'm breaking it up into 3 different lessons. The first lesson is going to be on the basics of magnetism. That's a relatively short lesson. The second lesson is going to be the longest one, and that's on magnetic fields and forces. And then the third lesson is going to be specifically on the magnetic field surrounding a current carrying wire and some of the applications of that. So this starts the first lesson, which is magnetic fields and forces. All right, so first some facts about magnetism. I think we've all played with magnets before, usually in the form of bar magnets. And what happens is when we hold 2 bar magnets together, depending on whether we hold the north end of the magnet next to the south end, or south to north, or north to north and south to south, different things happen, right? So the first thing that we want to note about any type of magnets is every magnet has 2 poles. It's got a north pole and it's got a south pole, right? And these poles can either repel or they can be attractive, right? So first of all, they have 2 poles, right? So we've got that. Second little thing is, as I'm sure that you already know, north poles, right? If I put a north next to a north, like we have in the situation down here, or a south next to a south, like we have in here, they're going to repel, all right? And so the only time that something can repel, or say if I move this very close to that, what would happen would be this magnet would move away. It would move in that direction as depicted by the blue arrow, right? I would also feel a force on that magnet, okay? The only time, if we recall from Newton's laws, that something can move is due to some force. There has to be a force in order to get something to change its velocity, right? And if something is just sitting there and it starts to move, it's obviously changed its velocity. So magnets, right? When we take 2 magnets, we put them close enough together, right? There is a force on each magnet due to the other one. So like poles repel, unlike poles will attract. We've all seen that, right? So probably nothing new here. And magnets create a magnetic field that surrounds them. So each magnet, right, again, each magnet has a north and a south pole. They have a magnetic field that surrounds them. And the magnetic field that surrounds any magnet, if you look over here to the left, right, we have all these magnetic field lines. The magnetic field lines leave the north side of the magnet and they travel around and they enter into the south side of the magnet, and then they don't just end there, but they continue through back up to the north side of the magnet. So every magnet has magnetic field lines. Again, they leave the north side, they travel around, right, because they are attracted to the south side, and they enter in the south side, they continue straight on, and then they leave the north side again. Right? So that's how the magnetic field lines look for a bar magnet. And they would be the same for any other shape, although sometimes the shapes can get a little funky, and so it's hard to tell which way the magnetic field lines go, but they're always going to go from north to south. Magnetic field lines also have a magnitude and a direction. And if you recall, anything that's got a magnitude and a direction is a vector, okay? So magnetic field lines are vectors and we have to treat them as such. Now, the magnetic field, or magnetic field that surrounds any type of magnet, whether it's an induced magnetic field or it's a magnetic field that is inside of a bar magnet, is we use the letter B to denote a magnetic field. So the magnetic field is given, all right, by the letter B. That's the variable that's used in an equation. And the unit for a magnetic field is the Tesla. right? Just like the car, the Tesla, well, magnetic field units are Teslas. So again, the symbol is B, magnetic field unit is the Tesla. So just what causes a magnetic field? Well, magnetism and electricity are extremely closely related. They are like brother and sister or brother and brother. They're in the same family. And just as an electric charge can be surrounded by an electric field, a moving electric charge is also surrounded by a magnetic field, right? But it has to be a moving electric charge, right, in order to have a magnetic field around it. So on the left-hand side of the screen, we see charges. These are static charges, a positive static charge and a negative static charge, and you can see the field lines around them. One of the main differences between a magnet with a north and a south pole that have the magnetic field lines, in fact, I'll draw one over here. All right, so here's the north end, here's the south end, and we have the field lines coming out of the north end and entering into the south end, right? Just like this. One of the main differences between a magnetic field and an electric field is that I can have just a positive charge, which has positive electric field lines emanating from it, right? Or I can have just a negative charge, which has negative field lines going into it or sinking it, right? I don't have to have a positive charge and a negative charge in the same situation, if you will, right? But a magnet is not like that. A magnet will always have a north pole and a south pole. So the magnetic field lines that leave the north side will always enter into the south side. If not the south side of the same magnet, if there was another magnet very close to it, they could enter into the south side of that magnet, right? But there will always be a north and a south pole to a magnet, right? You cannot separate north and south poles inside of a magnet. Now, electric charges that are in motion, right, will have both an electric field around them, and they're going to have a magnetic field. If we look at this picture over here, we see let's see here. We have a wire, say, and it is going from the bottom of the page to the top of the page. And let's say that that wire has a current running through it in the direction of the arrow, right? So we have a moving electric charge that is going from the bottom of the page to the top of the page. There's going to be a magnetic field that surrounds that wire that's going to look like the picture over on the right-hand side. So the green wire has a current going in the direction to the bottom of the page, and notice the direction of the magnetic field. Right? The direction of the magnetic field is perpendicular to the direction of the current. Okay, it's going in concentric circles around the wire itself. All right, so this is a three-dimensional thing. If you look at picture number 2 again here, I'm going to change the color to say purple. Picture number 2 over here, what we have is we have somebody's hand surrounding this wire over here. Right? We have someone's hand, they're surrounding the wire, and there's a reason for that. If I want to know the direction of the magnetic field that surrounds the current carrying wire in that case or in that case, what I can do is I can take my hand, right, and I can take my thumb and point it in the direction of the current, right, that is running through the wire, and then my fingers will curl in the direction of the magnetic field, right? And they can only curl in one direction. I can't curl my fingers backwards. So this is called one of the right-hand rules. There's actually 3 of them. This is the first right-hand rule, if you will. If you look on, if you look at picture number 2 here, it's got exactly that. It's got somebody's hand, their thumb is pointing in the direction of the current, their fingers curl in the direction of the magnetic field. If we did that for the picture in the right here, all right, I would take my hand, I would point it in the direction of the current, which is going down towards the left in my screen here, and my fingers would curl into the page at the top, and they would curl out of the page at the bottom. And that's exactly what's happening in the picture over here on the right. On the top, they are curling sort of out of the page, or counterclockwise, if you will, and they are going then they follow along the same direction, right? Counterclockwise on the top, and also counterclockwise on the bottom. But my fingers here can tell very easily what direction it's going to be. It's going to be this direction on the top and this direction on the bottom. It's going to take some time to really learn the right-hand rules. There's more than one of them. There actually are 3 of them when it comes to magnetism, but this is a start. So just what causes a magnetic field? Well, as I mentioned before, magnetism and electricity are very, very closely related. And they're so closely related that it really comes down to the atom and the parts that make up the atom, specifically the electrons. If you remember from chemistry, right, there are electrons, and you have different levels of electrons in the atom, and each electron can have a spin, right? In the picture that we have on the screen here, it can be either going sort of, if you look at the front of the electron, from the left to the right, or if you look at the electron on the right, it can be going from the right to the left, okay? And so those are 2 distinct spins. And if you look at the magnetic field that is caused by each spinning electron, the electron on the left here has a north pole at the bottom and a south pole at the top with the way that it is spinning. The electron on the right, is spinning in the opposite direction. It has a north pole on the top and a south pole on the left. Now remember that magnetic fields are vectors. So what happens if I combine these 2 electrons, or they're paired very closely? Well, their magnetic fields are going to cancel each other out, right? Because I have one with a north on the bottom and a south on the top, another one with a north on the top and a south on the bottom. If I add those together, those magnetic fields are going to cancel out. But that's what causes a magnetic field inside of an atom itself. It's the spinning of the electrons inside of the atom. And so if all of my electrons are paired, right, in their levels, in their shells, right, and I have this one paired up with this one, well, what happens to the magnetic fields that are surrounding them? They just cancel each other out. If I have a material that is made up of electron pairs like this, and they're all paired up, then that material is probably not going to have any magnetic field. However, some materials we find are quite magnetic, iron being one of them. And so if we look at the electron configuration of iron, what we found out is in the outermost shell, I have 1, 2, 3, 4 unpaired electrons. Right? Those 4 unpaired electrons are all pointing up, which means they have an up spin, which means they are creating a magnetic field, right? And those magnetic fields of those are going to add together, and therefore iron is a substance that can be magnetized, right? Or can have a magnetic field around it. We'll discuss just how those magnetic fields get put together in a few minutes. If we look, on the other hand, at copper, right? If you look at the outermost shell of electrons in copper, right? They're all paired up. Okay, and so copper is typically not magnetic. Now you do have 1 unpaired electron here, but it's not in the outermost shell, and so it's really not going to be magnetic. Okay, it's really the outermost shell electrons that are going to be determine whether an object is magnetic or not. Okay, so iron is magnetic. Copper is typically, well, not typically, but it isn't magnetic, and it really has to do, mostly to do with the electron configuration of those outermost shell electrons. Okay, so what actually makes a material magnetic? Well, inside of an atom, inside of a piece of metal like iron, you have billions of individual atoms, right? And those atoms have unpaired electrons. And so inside of that piece of metal, you have many, many, many things called domains, right? that have magnetic fields associated with them. If you look at this picture down here, what you have is you have a lot of different domains, and if you look at the arrows depict the direction of those magnetic fields, right? And as you can see, they're all haphazard. They're pointing in all kinds of different directions. And so this would be a piece of iron that is not magnetized. And the reason it's not magnetized is if you take the sum, the vector sum, of all of these things called domains, and these are magnetic domains, and you add them up as vectors, what you end up with is a net zero magnetic field for that particular material. Right? So this would have no magnetic field because they're all adding up, they're summing up to zero. And these individual blocks in here, these are called magnetic domains. Okay? And you can have almost an infinite number of domains inside of a material. So let's say I took a piece of iron that's like that has all these haphazard magnetic domains inside of it. Right? And I took another magnet and placed it close to that. And so I had magnetic field lines and that were going like this into this end and out of this end because I was holding another magnet close to it. What would happen is it would line up these domains that are inside of the unmagnetized iron. And what we would end up with is something like this. We would have a mildly magnetized piece of iron. If we kept that magnetic field close to that unmagnetized iron for a longer period of time, or the magnetic field was stronger, we would end up with something like this. And then if we removed the magnetic field, the external magnetic field from our piece of iron, we would have a piece of iron that is now has a magnetic field surrounding it, right? That would be like that, right? Right? We now have a magnetic field where all the domains are lined up, and it now has, if we took that piece of metal and tried to pick up a paper clip or something like that, our magnet that piece of iron could now pick up that paper clip. All because the domains inside the piece of iron get lined up, they create an external magnetic field, right, and an internal magnetic field, which is now useful to do some kind of work. What would happen if I took my bar magnet here and I split it in half, right, like this? Well, I would still have a north end and I would still have a south end for each piece of the magnet. So I can split that magnet up as many times as I want, and I cannot separate the north end from a south end. I'm still going to have a north and a south in each one of those pieces of magnets. So that's how we take an unmagnetized piece of iron or material and we magnetize it. Some materials are innately magnetized. You know, we don't have to line up their magnetic domains. Iron is not one of them. Iron you generally have to magnetize in some way. You take an external magnetic field, you put the piece of iron in it, and the iron will become magnetized. So this ends part one of basically an introduction to magnetism, what magnetism is, why electricity and magnetism are so closely aligned, and it's really because it's the tiny spin of electrons inside of an atom that create a magnetic field, and if we have enough of those electrons, unpaired electrons, inside of an atom, then we can potentially have a magnetized material. So again, this ends part one. In part two, what we're going to be doing is we're going to start looking at the magnetic forces that we have when we have magnetic fields and electric fields sort of combined together. So first thing we're going to look at is the magnetic force on a moving charge. But again, this ends session number one for magnetism. Stay tuned for session number two.